And today, Tim gives us an economic argument as to how we can build and retrofit buildings to reach net zero carbon emissions. All right, Tim, it's all you. Take it away. Thank you, sir.
Thank you, Freddie. Thanks for such a wonderful, glowing introduction. And I want to thank the USGBC for allowing me this opportunity to talk about a subject that is near and dear to my heart. And also, I appreciate everyone that's chimed in on this call, taking time out of your day to learn about this concept that we call net zero and how it can benefit all of us. I would like to start out first, though, by talking about some people I've admired and have influenced me over the years. Jordan Hyman, Bill Code, Bill Tao, Don Ross, and Joe Barazzini. These gentlemen were on the front line of energy efficiency and renewable energy when we were first awakened to the energy realities that erupted in the 1970s. Their leadership in the St. Louis region and across the country helped set a lot of us on this righteous path. They have given us a great foundation to build on. Let's do them proud. Okay, next. Okay, today we're going to work on paradigm shifting. How do we work on the structures that have informed how we do what we do? For many of these structures, we need to disassemble them and rebuild them to match the realities as they are, not as how we've been taught to perceive them. One of the most important such shifts I have made was occasioned by Buckminster Fuller teaching us to think about the earth as our spaceship, as it really is, in all of its natural glory. We need to really understand we're not adversaries. None of us are. We're all crew members. What do crew members do? They work together for the benefit and the survival of the whole ship. That's what we must do now across the globe, or the ship, as I would like us all to think of it as. Okay, so one thing is, I'd like to begin with a survey question. What would you consider, or your organization consider, to be a reasonable return on investment? Just want a brief answer, please. For instance, what is a decent 5-year performance on your stock portfolio, if you have one? You know, just something that you have as a benchmark that is what you consider to be a reasonable return on a solid investment. As you do that, in the Zoom chat feature, we'll continue. Take your time, think about it, but don't make it too long. All right, what's our problem? The emissions from burning carbon-based fuels drives climate change. We have to get to zero emissions. But when as soon as possible? When is that for you? Pick your target. Can we wait until 2050? I don't think we should gamble with the future of civilization. Let's do it as fast as we can. Okay. So what does it mean for buildings? Well, it's simple. Net zero approach balances the CO2 emissions with an equal amount of sequestered CO2. Generating renewable energies is relatively equivalent to sequestration if you're giving RECs to others. And what does it look like for our buildings? Well, if you start off and you look at the building budget, we have a faux building budget on the left there. It shows the current use in an average building of how energy components are fed to it and fills the effective energy bucket for that building. Okay, our usage includes nuclear, renewable, and the usual carbon suspects: coal, petroleum, and natural gas. Now, in getting to net zero, the first step uses cost-effective energy efficiency measures to shrink the size of the bucket that needs filling by 1/3. With reasonable energy efficiency investment criteria, we find that shrinking the bucket by 50% should be more than achievable. Howsoever, just looking at shrinking it 1/3 leaves 2/3 that we would like to fill from the renewable energy sources that we can reach. Wind and solar are currently our most cost-effective renewable energies. On building sites in urban areas, wind is generally not an option, and finding enough space to provide this from solar is often problematic. So, this energy bucket is generally filled with a mix of solar generated on site and the purchase of renewable certificates or RECs that were generated somewhere else. That's the reality today. So, looking at some terms and definitions we've got here, we've got net zero ready building and a net zero energy building. The important distinction between these two is that the net zero building has shrunk the bucket as far as is economically reasonable to reach the point where the cost of saving energy has a slightly better economic yield than the cost of generating renewable energy. Note that this point has been constantly changing as increasing in renewable generation efficiency and reductions in the cost of renewable energy continues. As this happens, the efficiency investment targets will continue to drop. So it's a dynamic thing that's being played, and it will play it back and forth. The net zero energy building happens when the shrunk bucket is completely filled with renewable energy and or renewable energy credits, certificates. So now that we've framed what net zero is, these are the steps we will try to take today to explain how we can achieve net zero cost effectively. So it's very possible. That's the answer. Two major myths are at work to try to forestall net zero efforts. Forestall implies intention. I'm not sure that there is, but that's the effect. The primary ones are net zero is way too expensive and net zero is too challenging technically. Well, the National Renewable Energy Labs in Golden, Colorado debunked these myths 10 years ago when it delivered a 362,000 square foot research facility on their campus in Golden, Colorado. They delivered this with a standard design, build, construction process that brought the building in at $286 a square foot. And that included all of the solar PV needed to make it net zero. The actual building costs were competitive with costs of similar buildings in the region. Definitely not demonstration. Definitely not state of the art. Everything that was done in those buildings can be done today. No new technologies required. Okay, so another myth that we need to bust is that companies and countries need to consume more energy to grow. To bust this myth, we need to look no farther than the US context. Today, the US uses about 100 quadrillion BTUs of energy to fuel our economy. That's the bracket on the right side. We fill this bucket by producing 95% of the energy in the US and importing 5%. Of this amount, if we want to look a little closer, roughly 20% is provided by nuclear and renewable energies already. These energies are CO2 free, carbon free. Now, of that renewable bucket, I want to point out that the renewables are now equaling the amount of coal that's used in the United States. But on further well, we're looking deeper into the renewable energy. 43% of the renewables is biomass fueled. This is still carbon-based, but is considered carbon neutral. However, this carbon neutral status only remains as long as we replace the harvested biomass with new plant growth. I need to point out that we have to have a positive approach to managing that. The myth is inherently based on the historical coincidence that energy use had tracked very well with growth in GDP. And this myth also supported the agenda of those who wanted to sell more energy, so that's why we kept hearing it. It is only coincident with GDP, energy use, because we choose to continue to waste energy at the same rates as we used to do at that time. In 1973, with the OPEC oil embargo, the cost of oil more than doubled, and the US, along with the rest of spaceship Earth, was thrown into a recession. This got our attention. Eventually, the price of oil dropped back below the price before the embargo, not just to the price at the embargo. Over the next 40 plus or minus years, we have effectively halted the growth in energy usage as economic growth has barreled along. By 2016, we had only added 1/3 to our energy bucket, while we grew the economy more than twice what it was in '73. Truly, going after energy efficiency has not hurt economic growth. Myth busted. Before we congratulate ourselves too much, though, on this feat, we do have to recognize that we can still do a lot better. Why is Europe so much more efficient than the US? The primary reason is that these societies are sending proper economic signals to the public. Energy costs a lot more there. While it is true that we are still harvesting efficiency at today's prices of energy in the US, if we really want to accelerate the pace to reversing the climate crisis, the US must send the right price signals. The incentive to accelerate change will only happen if we get people's attention at all levels. Increasing the cost of energy will get their attention. That's what happened with the oil embargo in '73. And look what that accomplished. So, topics for today. We've shown you how it is now possible to get to net zero. Now let's look at the economics, the efficiency of economics. The GDP chart showed that implicitly, efficiency is judged to be cost effective, or it wouldn't have happened. So what are the real economics of efficiency? Let's do a little bit more myth busting. It doesn't matter what anyone does. I can't have much impact on solving a big problem like this. It's been an explicit goal of the US economy since World War II to promote consumerism. This fosters buying more things, which fuels growth. The arrayed cacophony of marketing forces supporting this can be overwhelming. One of the casualties of this process is a sense of helplessness in the individual's ability to affect change. Well, as individuals, I want to point out to you and hope you take to heart the fact that you truly control directly 32% of the energy budget of the United States. If it's your residence, it's your transportation, you can have an impact, a direct impact. You also put an indirect pull on all the other sectors of the economy trying to have a job and buying goods and services. With 45 years of experience, however, I can tell you that it is cost effective with no new technology to work ourselves out of this mess. Today, there's a $3 trillion market in the US to just do what's cost effective. No new technologies required. And this is predicated on assuming a 4-year payback for business and a 6-year payback for individuals. As we invest this, as we make these investments in ourselves, it will help us realize that we don't need to rebut the climate denial segments of society. We will be directly rebutting them by showing economic growth as we reduce energy consumption across the United States. Well, with this kind of performance, you can see that we could easily reach guaranteed returns on investment. If businesses get 4-year paybacks, they get 25%. If we get 6-year paybacks as individuals, we get a 16% rate of return. These can be guaranteed. These are really readily achievable. Okay. Remember, no new technologies, very positive returns on investment. Let's go for it. Lots of jobs created, jobs. Please note that there are other reputable sources saying the same thing. McKinsey and Company in 2008, that long ago, 12 years ago, released a report documenting how the US could unlock energy efficiency in the US economy by deploying an array of NPV, net positive value efficiency measures that would save 18 quads of primary energy use and 1.2 trillion in energy savings. Okay? This reduces our bucket for the United States 23%. The opportunities that are cost effective today in 2020 for efficiency and renewable energy are even greater. So we should, updating their 2008 to 2020 will give us another boost. So I've been doing this a long time, so I look at this more from the standpoint of the Kyoto Protocol requests that we find ways to reduce our carbon emissions to 95% of what we were putting out in 1990. Okay? If we had a target that was reducing this 25%, as we could say we were asking for businesses, but it's general, we would roll emissions back immediately to the level of the mid-70s. Howsoever, we have a standard where we're trying to see that people invest in 8-year paybacks for efficiency and 12 years for renewables, averaging about 10 years. If we got the 10-year savings level, we would drop our consumption back to the early 60s. Amazing reductions in carbon, just for making stuff that's doing things that are cost effective. This would be a return on investment of greater than 10% the first day you get there. Now, how do we do this with buildings? To examine how cost effective this can be, we'll start with a residential example. Most of us are familiar with homes and their systems, so this will make immediate good sense to everybody. This is the Kimmswick home that Jordan Hyman and I built to demonstrate what we felt could really be done. It's a 3,000 square foot, all electric home designed with passive solar features. In addition to the passive features, there are other sustainability things that are key to its success. The first thing is we invested in insulated concrete forms. That's 2 inches of foam on both sides of a 6-inch reinforced steel concrete building. Effective R value of about 40. We invested in state-of-the-art technology in 2007, a ground source heat pump. The ground source heat pump is trying to reject heat to the ground in the summertime, but if we install a de-superheater that intercepts that energy, we can divert and recover that energy to our domestic hot water system. So we get 2/3 of the annual domestic hot water needed by recovered energy from the heat pump. because the building was a poured concrete building and doesn't leak very much, there's not a lot of outdoor air coming in, we have a whole lot more energy efficiency, but we have to give a little bit of that back up by using a ventilation system that keeps the air fresh in the house. Doing that, the air that we exhaust, we can recoup 50% of that out and pre-temper the air coming in, both winter and summer. Okay? We did, as I suggested, passive solar features, which are no more than, single glazed window, double glazed windows, sorry, we don't do single glazed anymore, double glazed windows on the south wall. We installed vacancy sensors so that people had to turn the lights on when they went into a space, but they would turn themselves off automatically if they left. And then we did 100% compact fluorescence in 2007 because LEDs weren't really readily available. Today, do LEDs. The net results of this is we achieve LEED Platinum status. And when we sent our numbers in, we have a rating at Energy Star 5+. But one of the things that matters the most is our energy bill. And taking a closer look at stuff that Ameren was publishing at the time to let us know how well we were doing, you can see that our home, my home as it's stated there on our bill, would use $774 of electricity annually, a 3,000 square foot home. They told us that the average home, similar to ours, would use $1,000. So we're using that in our economic analysis. Now, these are all good and nice, sustainable, tree-hugging, good things to do, but does it pay? Okay, let's take a close look at it. The similar base frame home cost would be $337,000. Research several years ago suggests building 3 homes in a Baltimore subdivision. They documented that the maximum extra cost you would expect for an ICF is 7%. So we're using the maximum. We asked the contractors to bid our mechanical system using both an air source heat pump and a ground source heat pump. At today's dollars, that would be an $8,000 premium to go with the ground source. The de-superheater to make the hot water would be almost $1,000 premium. So the net zero ready home, as we're calling Kimmswick 1, would be $370,000 roughly. That's a $33,000 premium over the conventionally built frame home in today's market. Now, we've got a $33,000 more expensive building. However, from a cash flow standpoint, your immediate premium that you see is the extra $6,600 that you would pay as a down payment on your mortgage. So that's going to put us in a net cash flow position from the first day, and we'll show you how that works. Howsoever, we could, if we chose to, immediately wipe out that extra $6,000 premium and down payment through the ground source heat pump tax credits from the federal government that are still available next year of 22%. In addition, Ameren gives us an incentive of $1,800. Note though that you can't always depend on these kinds of benefits because they're policy driven and policy can change. Hopefully policy will change to the better for us in the near future. Now, when you look at this, you will notice that we start off at a point down here of our $6,600 net in the hole extra equity that we had to put down on our down payment. So this curve on the right is the one I want you to watch. You're seeing gradual changes, okay, going forward. There are annual cost benefits for having done what we did, the extra dollars that we spent. The first one is a negative though, because we've got, you know, $33,000 more building that we built. Our principal and interest payments on an annual basis are going to be $900 more than the conventional home. But our average reduction in electric costs is almost $400. The insurance we pay is about $800 less. And then there are life cycle and maintenance costs on the heat pump system that save roughly another $400. Our net benefit is $764 a year on average. It varies every year depending on rates of inflation and stuff like that, but we've fully inflated it out and it's averaging $724 a year. Okay, if you look at this little curve here, you see this rises, that's 700 plus every year going up with the added inflation and the costs that we're saving, such that at the end of 30 years, you spent $15,000 less on your building than you would have if you had the conventional home. And it has, you know, $33,000 higher value just in its construction. Okay. In addition, beyond that, why were the insurance costs so low? Well, insurance company have loss experiences from more severe weather and fire events that suggest to them that reinforced concrete homes can survive these events with significantly lower claims. Less risk means lower rates. And I got these quotes from the insurance company that's, you know, operating our building right now. They gave us the differential, real market. So again, everybody's safer. Tornadoes, hurricanes, firestorms. Okay. So I think we've demonstrated clearly, at least with that one example, a deep dive and a thorough examination of all the pieces of all the layers of the onion that you can peel back to show what the real cost benefits can be. So I consider economics of efficiency resolved. So let's talk about the economics of renewables. Okay. Economics of renewables. This gives me a chance to slow and breathe. Okay, let's look at what the Energy Efficiency Administration of the DOE projected in 2015 would be the levelized cost of new generation built in the 2020 timeframe. Okay, now they used levelized cost of energy and they compared it to coal. See, coal is rated at 100%. So this is not just coal, it's conventional coal. It's primarily what's already built and what's being amortized right now. Now, renewable energies are listed there in green. And I'm sorry, let me go back a second. Just to show you, you know, geothermal is thought to be really low. Hydroelectrics is still better than coal. But back here, they still said that solar PV in 2020 would be not as cost effective as current, you know, coal produced electricity. Howsoever, 3 years later, after they published this in 2015, Deloitte came out with a global renewable energy trends analysis. And it said that wind is ranging in 2018 between $30 and $60 a megawatt hour. On the backslide, they were showing that coal was operating at $95 a megawatt hour. They also suggest that solar is going to be $43 to $53 a megawatt hour, and that conventional fuels would be producing electricity between 42 and 78 that they were, no, I'm sorry, would not be. I mean, these are not projections. I'm getting mixed up between my slides. These are realities. These were the values that Deloitte identified. this is where the DOE recommendation or projections of 2015 said things would be. This slide is not to show how far off the mark the EIA was just 3 years later, but to underscore the fact that the market moved faster than was expected to deliver lower renewable energy costs. I think that's a trend that we can continue to count on. Now, this slide just wants to ask all of us to consider the additional renewable energy opportunities that are out there, but that don't get much market play. They come from what are thought to be waste streams and are less sexy. That's basically why we don't talk about them very much. Lots of industrial facilities use natural gas for process heating in their loads. Most of this energy is a once-through process, and the majority of it goes up the stack. It doesn't do useful work. If this energy was first used to make electricity, and then the waste heat off of making electricity was used to provide the process heat needed, this would effectively almost double or more than double the value of the natural gas used in these processes. So CHP is something we really need to double down on and focus making happen in the US. This will be a dominant opportunity in the industrial market. Now, trash and garbage is something we pay to throw away. Okay, it's going to a landfill. Trash and garbage can be burned. Worst case, it can be burned to make, effectively renewable electricity. But at the same time, what it will do is it will reduce the landfill costs 90%. So as part of the solution sets for net zero, let's make it a priority to not waste these valuable resources. Now, getting back to the solar consideration, we're looking at solar, not wind, because wind is generally considered something that needs to be in a more remote location, not an urban site. So solar here will be considered to meet the load needs at various levels, and we'll tell you why we're making it at various levels in a moment, of energy consumption in this home. So you look at the fact that January is number one. We're using a whole lot more electricity in the wintertime. You see it ticks up back on month 12, and it starts the curve rising. But most of the energy is relatively flat throughout the year. We're not seeing the same increases that people normally see with air conditioning in the summer. It's because being ground coupled, we moderate or flatten out that curve. The only reason we have spikes in the winter is because the nature of the heat pump is it can't produce 100% of the energy needed for heating on very, very cold days. So we're buying direct electric resistance. Now, there's a couple of things that are really interesting and important for the grid and our neighbors. Number one is we're supporting all of our neighbors with any solar that we produce in the summer because we don't need much. Okay? We're grid supportive. We're also grid supportive in the wintertime because we're buying energy they're trying to sell when there's not much market. So it's a benefit to the utility company. Okay, so if we put solar in and we just want to not overproduce, we want to make sure that all of the electricity is mostly used on site, then we would only put in 6.5 kW to meet the needs of the house. One other reason we do this is because if we produce more than that, the net metering rules for Ameren, Missouri are, if you produce more than you use in any 1 month, Ameren buys it back, but they only give you 1/4 the value of that energy. They buy it back at wholesale rate, 2.5 cents a kilowatt hour. Howsoever, from a net zero standpoint, we might want to move forward with, oops, went back, sorry, and put in an additional 2.5 kW array so that we fully eliminate our electric utility bill. It means that we don't fulfill all of it with solar in the winter, but we've overproduced in the summer, and we move that green swatch above the red dots over to fill in under the red dots. So this means that we're now considered net zero without investing in other sequestration options or buying RECs. So what's the economic value of doing this? Hope that's readable. You can see that the cost is linear, and we've rated it at $3 a watt installed. That's comparable to average prices in the St. Louis, Missouri area. Now, with that, and I've shown the difference in the impact of the net metering here, because you see that things are not linear going down. We save less proportionately on the 9 kW than we do on the 6.5 kW for our annual savings. Howsoever, there are incentives that Ameren will pay you that are still linear, so you don't lose that. And the tax benefits that you get from the federal government are linear. Howsoever, just the cost of fuel benefits has put it in the scenario where if all of it is sold at retail value, or you're offsetting retail value from your Ameren costs, your payback is 9.8 years in Missouri today. Now, if you are upping yourself to the 9 kW and you are considering yourself totally net zero, you still have a handsome payback. It's 11.6 years, which is still less than the 12-year limit that we're asking you to consider investing into for renewable energies. That's an 8.6% yield. Now, Illinois Solar for All, going across the river, we're looking at a industrial plant that we worked on, and it would accept readily, based on the size of lot lands available to it, 520 kW. It would cost a little over $1 million to install it. You get annual savings. You get a big Ameren incentive for doing it. And there will be what are called solar renewable energy certificates. We'll talk about those a little bit later, that are available to you. Ameren, Illinois, by state law, needs to meet a 25% renewable portfolio standard. To do that, they are also required at this point in time to fund other entities to install renewable energy, that they will then buy those RECs from them. Okay, this is the green component of the green power that you're producing, not the electrons. So with that, Ameren's going to buy 15 years of those, but they squeeze them into 5-year payments up front. And this shows the value of 2 years of payments. I did that because it showed what was needed to reach our 2-year payback. I didn't want to do a lot of columns to show you this, but that's a 50% return on investment. Year 2, paid back. Howsoever, if you wait 3 more years and you take the RECs, you've effectively eliminated the cost of your system up front. You get $50,000 more than it took to purchase and install it. There's no reason why you couldn't be doing solar in Illinois, except there's so much demand for it. You're in a long line waiting to get a hold of these benefits. Start sooner rather than later. So I believe that answers the question of the economics of renewables. I consider them to be within economic reason today in the St. Louis market. So let's define and look at the RECs and other offsets and things like that that we were talking about. Okay, so Renewable energy certificates are the green component of the value that they can, in effect, separate from the actual electrons generated from the renewable energy process. This is all bookkeeping. It's not a reality, you know. No real electron is greener than any other, but no respectable electron would consider itself greener than any other. Too bad, Kermit. It has market value because policies that have been established require utilities to make sure that they are generating renewable energy as part of their power generation portfolio. If they cannot or choose not to produce renewable energy, they can buy the green component from other entities that are generating it. With this market now firmly established, there are many opportunities to sell these RECs to people seeking to be net zero, but for some reason can't get to it on their side. Here are many of the reasons. Okay, this slide demonstrates why entities that want to be part of the climate solutions might need to buy RECs to demonstrate their net zero commitment, especially if they can't produce it themselves locally. Buying RECs will allow them to participate with the larger community. This purchase will support others located in areas where they can economically produce an abundance of renewable energy. It's a team effort. The crew members are working together. As mentioned before, or maybe I forgot to mention, our homeowners association has policies that kept us from being able to put solar on. And the net metering issues that I've listed here also can affect the decision to go for renewable energy on site. But since our homeowners association would not allow us to put solar on back then, which was really expensive back in 2007, we chose to purchase what are called RECs. And they were being sold by Ameren through what was their Pure Power program then, and it cost us $0.015 per kilowatt hour. In other words, we added almost 20% to the cost of our electricity in order to claim that we're renewable or net zero, okay? Today, in the 2020 market, Ameren will sell you the same Pure Power RECs for $0.01 a kilowatt hour. So it's showing the anti-inflationary nature of how much renewable energy we're producing that the RECs can't command a market value that's still current with 2007. The price has gone down. Okay, now another local example that I think is important to illustrate this is Anheuser-Busch InBev owns or buys RECs now to replace 100% of its brewing energy used in the US. The two examples are, A, they're in partnership with an Oklahoma wind farm that can wheel the power to their plant in Houston, Texas, or other places, okay? Now, this has to do, again, with policy decisions. Texas and Oklahoma are deregulated utility markets. Missouri is not. So in Missouri, they can't wheel RECs to us or wheel the actual electrons to us, but they can give us RECs, and they buy those RECs from a solar farm that's in Pecos County, Texas. So those are, two ways that you can see make sense based on market requirements. One, we can get the electrons there, so we want to use the power directly. Two, we can't get the electrons there, so we want the RECs. Okay, offset. Now let's take some design steps to net zero. Look at that. So this slide is a little bit dense, and this is set up for new construction. The renovation process will be slightly different. We'll show you that on the next slide. The first thing I think that is most important is establish a smart energy investment policy. And you do all the normal things you do in planning in masterminding a policy, we're just adding the energy components to it. You establish your energy project requirements, but you're also going to review the site if we're going to be required to install renewable energy options. So there's a site energy analysis that goes in that's deeper than what you normally do on a site. I would also recommend that any building done implement the advanced in commissioning process during the design cycle according to LEED. This gets another pair of informed eyes working with the architect and the engineer to make sure that all energy opportunities are taken maximum advantage of. You have to base it on some code. Most of us are on the International Energy Conservation Code. That becomes the building baseline for the model that you're going to compare yourself to in order to strive to use design to achieve net zero. Okay. The energy efficiency target that you should set should be at least 30% less than that allowed by the code. You're going to compare the baseline building's energy use and energy costs to the actual design for compliance with the energy policy. Then you're also going to design and evaluate renewable energy for also compliance to see if you can actually fill your entire bucket by making the building more efficient and then using renewable energies on site. If you can't, you'll have to go into a REX mode. And there are opportunities to do it multiple times, but then you're going to eventually execute. But after you execute, you need to measure, verify, and educate. But we're following an energy policy that we've established, which we'll talk about in a moment. For renovation, you don't have to build a straw party to compare yourself to. You've got an existing building. You document your current energy and water use and any renewable energy production that you have on site. Then you perform an ASHRAE level 2 energy audit. You interview, you pick the best ideas that the maintenance and engineering staff have already come up with, and you try to present them in a cost-effective manner to the owner. Developing measures for efficiency and renewable energy as you go along. Again, execute, measure, verify, educate. Now, let's talk about this energy policy. The energy, again, it's about mindset. We don't, in my mind, need to be motivated to save the planet to do these things. We can simply be motivated by greed. We can invest so that we no longer waste our money on bad energy practices. Reaching these reasonable rates of return on investment will make sure, however, that we truly are saving the planet. No pain required. Painless. I feel like I'm in MASH. Anyway, what rate of return? The questions you really need to get into and expose to yourself, for yourself, and for your entire organization, why you want what rate of energy return. What rate of energy return do you think is reasonable for renewable energy? And why? Then you have to, of course, decide on whether or not you're going to apply more program opportunities to yourself. You're going to try to go for LEED, or you're going to do the, oh, I can't, I'm drawing a blank on the building program that is restorative. I forgot the term for that. It was there this morning earlier. And then you're going to base it on all the many layers of the onion that we peeled back to show you are useful to apply to evaluating, improving the performance of your building. You build a high performance building, and not only is it going to perform in a high manner from an energy standpoint, it's going to perform in a high manner from an economic standpoint. So also make sure you implement and designate a critical time frame for getting all of this done. When we've helped clients do this in the past, often the motivating thing that has, the non-motivating thing that has kept things from moving as fast as they could is setting goals and time limits for energy efficiency improvements. So you want to set clear reductions by a date certain. Okay. Again, we'll just start and we'll look at it. Well, we'll go through it in detail. This is what we would suggest be a sample smart energy investment policy. It has to be specific, measurable, achievable, realistic, and time bound. If we don't have that, you don't have closure on a policy and a system for making this happen. We strongly recommend an 8-year payback for energy efficiency investments and a 12-year payback for renewable energy. You want anything you do to be at least a minimum of 30% better than the codes. And then again, the timelines that we're talking about, I would have a minimum of 20 years. If you've got a 30-year mortgage, for instance, I would use the 30 years like we did on the Kimswick house. And we evaluated first costs, energy costs, maintenance costs, life cycle costs, inflation. And one of the things we would recommend now that you do is place a 20-year value of carbon that you saved at $20 a ton. If you add that up, you're anticipating what the value of that is already in the voluntary markets around the US and the rest of the world. So at some point in time, we're going to be able to generate our own energy efficiency credits that will have significant market value. So I'm trying to prep everybody to be ready for those markets. Again, if it's an existing building, not new construction, we want to make sure that we reduce existing energy consumption at least 30%, and we want to do it at least within the next 3 years. That way, the studies that your energy consultants do don't gather too much dust on the shelf. So let's commission everything. Let's measure, verify, and educate. So now this is addressing from the designs point that, again, we're in the design section. You want to pay attention very much. I'm just putting the site model up here so that we can talk about site. You need to orient the building properly on the site. Make sure all buildings are optimally oriented to the sun to better minimize environmental energy loads and maximize energy efficiency. Make sure that passive design principles are not ignored. Too often, architects, for some reason, choose to site buildings differently. Some reasons are valid, many reasons are not. But in any case, you can always respond by orientation to more or less windows. You don't have to be uniform on all sides. So then you also will evaluate the site for what renewable energy production opportunities exist to finish filling your energy bucket. Now, there needs to be a holistic integrative design approach driven by sound economics. Everyone has something to contribute. All of us need to be involved. All hands have to be on deck. Batten the hatches, luff and stow the sails. We need to eliminate all waste. What has happened in the past isn't working. We need to disrupt the current processes. For instance, if we're talking about economics, we've got first costs, energy costs, maintenance costs, and life cycle costs. Okay? These shouldn't be in their separate silos. We have to refashion our ways of thinking about paying for things, destroy the silos and their compartmentalization, and make it an integrated process that understands the interrelatedness of costs over time. Make decisions today while being mindful of our impact on the 7th generation to come after us. Build for the future. We've already shown that it's cost effective. Why aren't we doing it? Okay, there's a few other myths we need to bust on the engineering side. If some is good, more is better. Bigger is better, and less equipment is better. Au contraire. You've got to be sure that you know when to stop, and you use the guidelines that we've given you for efficiency at 8 years to make sure you don't put an extra inch of insulation in when it's not paying for itself. Each inch of insulation will save less energy than the inch you put in before. Bigger is not better, bigger is only bigger. And typically that means it's oversized and it's going to be wasteful. It's going to be less efficient. Okay? You don't want to spend more money on equipment you don't need so that you can have lower efficiency and higher energy costs. Less is better. Well, we've already shown that, we've already stated, and it's a fact, that your building and its equipment goes from 0 to 100% of your loads, both for heating and cooling. If I have one piece of equipment at 100%, a lot of the hours of the years, it's a lot less efficient than it could be. If I buy 3 modular pieces of equipment that give me the same output, I now can follow the loads a lot more efficiently. Yes, it may cost more to maintain 3 pieces of equipment than it does 1, but your energy savings will more than offset that maintenance cost. In addition, more pieces of equipment give you higher resiliency in case one goes down. Oh, this is another good one from our buddies at Facilities Net. We saw them earlier with the NREL building. Only design matters. Operations don't count. No. The design gives you the opportunity to be efficient. It's operations that maintains your staying efficient. You got to do it. You could lose 30% in the first year just with people resetting points on temperature in different offices to make the tenants happy. Okay? If they don't get reset to where they really need to be, you lose that. In addition, beyond design and at a more ephemeral level, you need to keep plans on track and create staff incentives and rewards for maintaining performance. Invest in your people, give them a reason to make sure it stays where it needs to be. They're your eyes and your ears. Let them do their job, but make sure that it's rewarded when they do it effectively. Okay, now let's look at some quick case studies. This shows what has happened at the Danforth Center. They expected to be very energy efficient. However, design problems thwarted that attempt. We were asked to assist them and tackled 2 major issues. They were using too much outside air and the boilers were way oversized. Again, bigger is not better. Okay? We dropped the outdoor air intake from 15 to 8 air changes an hour, almost cut it in half. We tore out 3 10 million BTU boilers that were so oversized they could not stay and operate in the summer during the reheat loads. These were replaced by 4 2 million BTU boilers. We went from 30 to 8 million BTU boilers. Okay, and they were condensing. The original boilers were not condensing. The green line shows the cumulative savings, and the red line shows the cost of making the investments in energy efficiency. The total spent over the 10 years we were involved doing that paid back. Well, the 10 years didn't pay back, but the first start paid it back in 21 months. And after that, we had more than enough money to pay for the other improvements. They eventually spent a total of $600,000 and saved $2 million. This netted a 34% average ROI over 10 years. They cut their carbon emissions 20%. On the WashU campus, Brower Hall was already LEED Gold when we started working on this building. We were doing minor tweaks, okay, on the control system. We did more than just minor tweaks on the controls. We did some other investment in other things, but the overall return on investment was 40%. It paid back in less than 2.5 years. We saved 25% of the electricity and 44% of the natural gas. Most of that was due to moving less air in the building. We dropped the airflow in the building 34%. By doing so, since all the air was sent out at 55 degrees and reheated when too much air was delivered to the space, we sent out 50% more air than was needed at 55 degrees, and then we reheated it all back up to space comfort conditions. We also saved 28%. Shows how simple things can be, doesn't it? Eden Theological Seminary, been there a long time, had massive steam boilers that were heating all the buildings off of this plant. They had a problem. They were sitting on, not invoices yet, but estimates of cost to renovate their system, maintenance and repairs of $150,000. And they asked, what could we do that would be better? So we converted from steam to condensing hot water. You don't need steam. Steam is inefficient by its very nature. It's too hot, and you don't need it that hot. That's a simple way of putting it. But we also had to not just convert the boilers, all the devices that were using steam needed to be converted so that they could use hot water. We did all of this in less than 6 months. It was a massive effort to try to get it done quickly because they asked in April and they wanted heat by October. And we made it happen. So they reduced their natural gas usage 66%, saved 65,000, reduced CO2 by the same 66%, but that was equal to 528 tons. Spire was tapped and they paid them a rebate for their efficiency efforts of $66,000. They ended up with a return on investment of 16%, 6-year payback. And that's less than the 8 we would have suggested. And these savings, by not having to spend money on that fuel, the $65,000 that they saved, effectively increased their endowment by 1.3 million. Now, this just shows a curve of the 2 years of data prior to our effort. Just there, you can see it bounces around a little bit. There's some operational issues about how it's using energy, not great control. That's because I see a lot of vertical variation. Now, this is the curve of the year after they did it. Notice how tightly the points hold to the curve. We're in tight control at this point. But the red line lets you graphically see, you can now understand saving 66% of the energy. Again, measure, verify, and educate. Now, when we look at Central Methodist University and their classic hall, I'm showing you the before and the after stacked on top of each other. You can see they were all over the map. There was no reason, no rhyme to why they consumed energy in the building. The controls were really upset, you know, and we gave them a big dose of, I guess, Pepto-Bismol, you know. So now you look down there, you can see the actual operating data are clinging very tightly to the line. Okay, this was a recently renovated energy for efficiency. This historic building, they built out on the inside and they insulated the brick walls and they installed ground source heat pumps, state of the art. It's an all electric building, But what triggered our getting involved was they were really upset about how high their energy demand costs were all around, all year long. And you can see, we're not going to have that same issue. What they did was we reduced energy use 55% for the kilowatt hours, saved $26,000, and had a 55% savings of CO2. Okay. I want to point out that all the examples I've shown you were intended, except for Eden Seminary, were intended to be state-of-the-art opportunities, recently built, not ancient buildings. And look at how well we were able to get them to perform. I think I can support from this that it will be not unreasonable to expect that you can achieve 50% savings if you have an 8-year payback. All of these paybacks, this was, I'm sorry, we didn't put it here, but this was a less than 2-year payback for Central Methodist University. Okay, now we've seen this thing done at unit levels, and now let's look a little bit at how we can scale it. The next step we need people to think about is scaling the solution. So again, there's our model. Okay, it can show what is available and the interconversion steps that are needed, what we should do about storage, or should be analyzed, and then how that's going to fulfill your loads required. Okay. Now, this was a neighborhood that we did an analysis of for a community energy system back in 1981. It was 168 dwelling units, and our remodel efforts suggested that we could reduce the heating costs in the site 50%, as well as the cooling costs, just with thermal transmission improvements. And passive solar in the winter would drop the heating costs another 20%. If we redirected the neighborhood's costs for disposing of waste, sewage, biomass, trash, and garbage, we could generate the energy needed. Back then, we didn't have a solar option. It'd be a whole lot more cost effective if we had already been able to put solar on at the 2020 price and efficiency levels. Our cost estimates back then suggested that it was a 20 to 30-year payback. Not bad for a neighborhood, especially if you're working to try to be net zero. Still doesn't meet our criteria, but if I redid this today, it would probably be a lot more cost effective. Again, taking waste and going to energy, combined heat and power again. We can burn this. We can reduce landfill waste. There are multiple of these in the United States that are burning municipal solid waste. In Sweden, they work at slightly smaller scales so that they're more community oriented. In Sweden, the law says you cannot landfill any organic waste. You do have to burn it. So these become, small DERs spotted around the countryside supporting each other. And in addition to just burning it, we can make renewable natural gas if we use anaerobic digesters or some other incipient technologies to convert fuel like sewage, animal waste from CAFOs. And there are other additional benefits in terms of nutrient recovery that you can make for the ag sector and co-products that can be used also in the ag sector. Now, a small town in Texas, Georgetown, Texas, about an hour north of Austin, used PPAs, power purchase agreements, to install 144 megawatts of wind in North Texas, 150 megawatts of solar near El Paso. The ERCOT transmission system in Texas could easily wheel all that power to Georgetown. Through the PPAs, they had delivered to their gate more power than they needed at 4.5 cents a kilowatt hour. They added a little bit to it for maintenance and distribution, and it was now significantly less than the former power they contracted for from the grid. At the end of the PPAs, the city can own the assets. Unintended consequences for the environment are, it saved lots of water. It takes a lot of water to make a kilowatt hour. These are not made using conventional processes that require cooling. Next steps are to figure out how to store this energy so it's always available. It's dispatchable. Now, having gone through the renewables and talked about them, I can tell you that there's a curve, and we're on that curve. Eventually, we'll be mostly renewables. Right now, we're mostly non-renewables. But that little dot tells you that the world at large is somewhere between 18 and 20% renewable right now. Just like the United States is 18% non-carbon generated, although I don't consider nuclear a renewable. So a couple remaining obstacles and things to talk about. Some of them are real, some of them are imagined. Cost effectiveness and financing, technology, management's perceptions and motivation. Well, cost effectiveness, I think we've already dealt with that. We know that it's cost effective, okay? Financing. As for financing, there's a large array of means and measures to pay for both efficiency and renewables. A PPA, for instance, tackles renewables as a market, and the Energy Services Agreement, the ESAs, tackle efficiency. These two programs alone will provide 100% of your financing and no dollars up front. You only pay for the energy that is either saved or delivered. And they got to document that to you. So it's a no risk opportunity. And with that in place, among all the other opportunities that we've got with incentives and tax credits and stuff like that, it's clear that there are no credible barriers in financing going forward. The technical solutions, not an issue. No new technology. What's available today is already more than cost effective. Technical solution to problems are continuing to evolve, becoming more efficient. LEDs and solars are good examples of that. History has shown that technology will get even more cost effective. The real issue is perceptions and motivation. We're in an age of misinformation. There are powerful political and economic agendas behind climate denial. Competition for the attention of decision makers above the din of that noise is the real issue. We got to compete with that. Old habits die hard. We've never done it this way. Silo thinking, we've already talked about that. When you have an integrated energy and economic expertise on your team, you've got the champions that will make it happen in your organization. Foster that. Establish, again, a smart energy investment policy. Link management incentives to achieving the energy goals and make those same incentives, go down to the ranks. Corporate education and training is required to make this sustainable. And you do have to invest in the energy skill sets of your staff. There are many benefits beyond financial. There's marketing benefits. You diversify your energy supply. You've improved your resiliency. And it's just a nice feeling to know that I've improved my own energy efficiency. You're also mitigating the climate risks, and you're improving the overall community environmental quality. So we hope you've benefited from this presentation. We believe that we've shown that the value of establishing energy master planning guided by smart energy investment policies will generate significant benefits. Digging deep into the economics makes sure that you can show other people that it is cost effective for you to reach your net zero goals. There are investments out there that will add value to your property, and money that you save will grow over time as fuel costs increase. So it's not a static benefit. It's an ever-increasing benefit. Approaching the problem holistic, busting silos, is a great way to make sure that your methodology will succeed. That the cash flow in your current energy and waste bills, along with financing options available to you, can make sure that you implement your net zero solutions and immediately find yourself in a cash flow positive mode. I thank you for your attention. Just want to remind you, it's in our hands and it is up to us. Hope there's some time for questions now.
Tim, thank you so much. That was a great presentation. This is Emily chiming in here. I'm going to manage the Q&A as best I can. We do have a few minutes for questions. And Freddie had noted a couple that came in earlier. I just wanted a couple points of clarification. First, Mark Lapata asked about the Ameren credit that you mentioned when looking at solar in Illinois, the $125,000 credit that you mentioned. Do you have more details on that? Or
that's deep in the weeds. Thank you, Mark. But that is what is their smart inverter rebate for that size system.
Great, thank you. And then early on in the presentation, Ralph Bickness asked, based on the equation that you shared on net zero, it looks like you're defining it based on operating energy. What about including embodied energy?
We were taking this from the standpoint of, again, site and source-based energy. We have not looked at embodied energy. Ralph is very famous for the Living Building Challenge, which was the thing I was trying to state earlier that I couldn't get out. And in achieving those levels, that's why I was suggesting you have to consider what level of program you're trying to achieve in this, whether it was LEED or Living Building Challenge. No, this did not include embodied energy. That's a level of investigation that takes more time than I think most people can afford.
Agree, it is a much more complicated endeavor, but also very important.
Very important, but I'm looking, I'm motivated by the 80-20 rule. We're nowhere near the 80-20. Okay.
Yep.
So I'll yield the 95-5 to Ralph.
Great. And then one other quick clarification on the Kimswick house. The walls are ICF, insulated concrete form.
Yes.
How was the roof insulated?
Well, the roof we'd taken it up to an R30 with cellulose insulation. The roof itself was not insulated. The roof was a vented space. You know, the volume. We just insulated the ceiling to an R30, which we consider to be, you know, sort of the maximum benefit that you can get trying to follow the standard that you don't want to over insulate because the next inch doesn't get you much.
Got it. All right. If anybody has a question, if you want to maybe raise your hand, or we can take a couple questions, I think live even.
Cool.
I see that Ralph did comment that LEED is now incentivizing life cycle analysis, specifically reducing
cool.
carbon in material by including credits for LCA. So that's in LEED version 4, which is great.
Indeed it is.
Let's see. I'm not sure. I can't. Anybody have any questions they want to ask?
Tom Brayford here. Really great, Tim. You were one of my very first inspirations in all of this, and I'm glad to know that you're still around and doing more than ever. My one question is that one of the challenges I see in the development world is that a lot of investors now are looking for a 3 to 5 year turnaround on their money, and that just doesn't give us enough time to make this work. how do we convince them they ought to maybe invest in opportunity zones and do a 10-year hold?
You know, Tom, you got me there. I mean, I don't play in that realm too often, but I would think that a general solution to all of this is one of the ones that I mentioned early in the presentation, and that is we have to make energy truly cost what it's worth. We have to send market signals, and we can do whatever we want later with the benefits, but if you increase the cost of energy, you also shorten the lifetime of the value of recovering the investment and the savings. So that would be my best response.
True costs, that's what we need to be looking at, right?
So demonstrate that it actually pays to go for the longer term gain.
Well, I mean, it could be shorter. It could still be the same shorter term gain that they want. It's just that the energy is costing enough that the time frame for recovery is less. Let them still have their 3 to 5 years. I mean, if I get 3 to 5 years, 5 years is great, because most of what we've identified is paying back in less than 4 years. So I don't see that as an issue. But the 3 years, I think, is squeezing it tighter than we should with the realities that we're now facing.
May I chime in something?
Sure.
Thank you, Tim. Wonderful presentation and career, and I love you.
Thanks, Jim.
So, of course, PPAs are long-term investments that we have investors working on all the time with on our clientele. And that, you know, they start at 15 years with immediate savings to the end user. So that's another answer to time.
Right.
I see that Ralph put a question in the chat. Ralph, do you want to elaborate on that? The 30% below question?
There, I had to take myself off mute. Yeah,
Cool.
thanks, Tim. Excellent presentation, really insightful. So thanks a lot. Just
Thank
you mentioned a goal of 30% minimum below energy code.
Right.
And I just was curious where that number came from, whether it's kind of arbitrary or you find it to be a good economic kind of threshold, or just, you know, kind of what's the justification for 30%, say, versus 20% or 50% reduction?
Well, it's all predicated on what you have established as your economic criteria. Okay. My recommendation is 8 years. Okay, so that would have the ability to probably easily get to the 50%, perhaps beyond, past the 50%. The 30% floats around based on my years of working with ASHRAE on the 90.1 standard. And the fact that you need to understand most of these standards are developed in what's called a consensus process. So a consensus process will generate not anywhere near the state of the art, even the cost-effective art. It's going to be set at a level that captures only the most egregious offenders and makes them try to do it somewhat right. So I think there's room in there. And I believe there are extra points, or there's something in the LEED process that jogs my mind that says 30% less is a target. And in that process, you know, I keep hearing 30% in a lot of places. And I also mentioned 30% to staff, and they say, you don't want to sound unreasonable, don't go beyond 30%. So I can readily stand behind 30% without any equivocation. So I guess that's a long-winded explanation of why I'm there. Thank you, Ralph.
Yeah, we do have an institutional client that we both have worked for that has that threshold as kind of a minimum. So they don't I don't need to mention their name, but that's one of their thresholds.
Right.
So they found it to be reasonable.
Yeah, that's what I'm saying. I don't think it's unreasonable. So I don't get slapped.
Great. We have one more question in the chat that I'm gonna take, and then we're gonna wrap it up and let Freddie make some closing remarks. But so Richard is asking, as solar energy becomes more popular, will Ameren tend to reduce the future payouts for energy return to the grid, or will they embrace the individually produced solar energy trend? I guess this is like putting on our crystal ball, maybe.
Well, I don't have a crystal ball. And I know it's going to have to go through a MIA process. And I would recommend that anybody that wants those sorts of things to happen, they participate in the comment timeframes during MIA to see if we can build support for things that are going to effect better results for the planet, however those turn out.
That's a great point, Tim. Just for those who aren't aware, MIA is the process that Ameren, I can never remember what that acronym stands for because there are like 3 different MIAs, but it's at the state level that that Ameren negotiates their incentive programs, basically.
It's Missouri Energy Efficiency Investment Act.
There you go.
So I'm so proud of the state that it actually considers that there should be energy investments. That's part of what I've been trying to achieve for 45 years. Have people really view energy opportunities as true investments in themselves. So I get wound up.
No, it's good. That's good. All right. Tim, thank you so much for the presentation, and to all of our friends at Energy Resources Group for being a part of it, and all of Tim's pals who joined us today. Freddie, do you want to wrap us up?
Sure, yes. Thank you. Yes, thank you so much, Tim, for presenting, and Matt and Aaron. I just wanted to share a few things. When you registered for this event, you may have noticed there was a member rate and a non-member rate. So I'm going to share in the chat a link to how to become a USGBC Missouri Gateway Chapter member. And then also coming the end of the December is the last day to become a Green Schools Quest mentor for our spring 2021 program, so which runs just January through March. So that's helping local schools in our area put on sustainability projects with their community. And then lastly, Tim, one of our founding members of USGBC chapter, our 20th anniversary is in 2021, and we're kicking it off with our State of the Chapter and Social, which is going to be the second Tuesday of the month, which is when we always have our educational program. So keep a lookout for that second Tuesday on January 12th. So the link is in the chat now. So go ahead and register, and we'll look forward to seeing you all in 2021. Thanks so much.
And again, I'd like to thank everybody for their time, consideration, and attention to something that's so close to my heart. Thank you.
Yes, indeed. Thank you all so much.
Thanks, everyone. Have a great holiday season. Stay warm out there.
Bye. Thanks, Tim.
Thanks.
Okay, gonna go ahead and end it. Thank you guys so much, Tim. I really appreciate it. This was awesome.
It was a pleasure. Thank you for making it happen.
Yeah, we did record the event, so I'll get that to you soon.
Very good.
All right, cool. Thanks, guys. Bye.
Bye.